Good afternoon, everyone. Thanks for coming to this session. So today we are going to, Pablo and I were going to talk about the heterogeneous training cluster, which is Ray and Netflix. So both Pablo and me are from machine learning platform group in Netflix. So this is actually the homepage of Netflix. So if you are a Netflix member, you probably already found out that the homepage is highly personalized for each profile. So our overall goal is try to enable our user to find the interesting contents within Netflix homepage. And the personalization actually is the core pillars because it will enable the user to have a different view of the content, which actually adapts to their interest and even extend their interest over time. So in short, in Netflix, everything on the homepage actually is the recommendation. So it could start from the how do we construct the page for you. So if you see the selection and the placement of the row types actually are highly personalized. So there are like tens to thousands of different rows in our database. Basically, so if you say you are a super fan of the documentary kind of movies, so you may see that kind of rows will show up at the top. So when it comes to each different rows, when it comes to which titles we want to recommend, so we have the video ranking algorithm to sort out the different videos in each row according to your test. Yeah, even for the same videos, for the same movies, so we have a set of the artworks, which is also customized for your test. So you can choose whatever according to your long view histories. So let's talk about the Ray. And so first I want to give an overview of some performance optimization for the model training systems. So this will help you to see at a glance of why we use Ray. So I will mainly talk about from different aspects of the model training system, like the computation, communication, also the file system, I/O. First, let's dive into the training workload calculations. So we have different workloads. The first one is most heavily used is our recommendation use case. So the model is more like a DRM or like the deep and wide model architecture, which is featured by the sparse embedding tables and concatenated with some dense features and then plug into the multiple perception MLP. So normally for this kind of models, we have a very large data set, but actually we have a relatively small model training time because it's more like memory bounded. So the embedding lookup is super fast actually. So and normally in order to reduce the training time, so we normally use the multiple GPU distributed training. And it turns out the gradient communications pop out as the bottlenecks from time to time for different kind of training models. Another big category is the media ML use case. So our internal researchers use the multiple models with the constructive learnings to learn the semantic representation of our content. So the data source is already very diverse. We have the text, images, audios, videos, and etc. And also because we always try to divide the long format videos into different samples. So this will result in a very, very large data set basically for all the assets we have. And again, we also have to use the multiple GPU training and with some distributed data parallelism to speed up the training. So the last is more like an emerging use case is the large language model fine-tuning. It's a small data set, but it has a very long model execution time. And also, sometimes it's very hard to fit some models into the single GPU memories, especially the 70 billion, the Llama 2 models. And also the computation is really computation intensive due to some transformer-based architectures widely used in this architecture. So in terms of computation, so we use the custom operators for to improve the computation efficiency. As you know, it's always very hard to compose some desired operations in a very efficient way. I think this can be like from, like the very high framework overhead. If we have a lot of tiny ops to compose a very complicated operations, and also for each different small operator, it always involves a lot of memory allocation, deallocation due to the model training runtime. And also another opportunity is like we fuse a series of operators, sometimes for better performance. Like this sometimes is not supported by the framework like the PyTorch and the TensorFlow. Yeah, a very interesting example like we have basically have two embedding tables, and then we have look up some entries from this embedding lookup table, and then do the dot product. It's more like a reduction, and when we fuse all these operations into one single op, we can get like 2 to 3x speed up of the training time. Yeah. The second item is like we always adopt state-of-the-art operator from OSS, no matter whether it's from PyTorch or TensorFlow. For example, we adopt the table batch embedding, which actually is used in Meta like for the production, which to replace the native embedding back of PyTorch. Another one is XFormos, which is also pretty popular in the PyTorch community because we have a lot of like legacy models still in TensorFlow. So we still try to develop some TensorFlow operators from this, the Kulas-based implementation of the flash attention to speed up our TensorFlow models. So this will result in much less memory and faster speed, which allows much longer sequence. Yeah, the second one is the GPU communication. So as you know, like the dense weight gradient, like all reduce, is actually it gives very great performance thanks to the optimization of the in TensorFlow or PyTorch. However, for the sparse weight, like the embedding table, so this which is widely used in the recommendation use case. So this really have very different performance according to your different model size, batch size. So we have different solutions. For example, the first one is actually native TensorFlow. It tries to gather all the activated indices, try to deduplicate the same index and do the segmentation sum for the gradient computations. This actually could be the bottleneck if the batch size is large, because there's so many indices for different GPUs. You have to gather them together and then do the update. And another solution is like if the table is not that large, actually we can use the dense method to do the table or reduce. This is also supported by Horvath support. I think the last one is most probably for the large table like the sharding. This can also be used for the small embedding table. Either you don't need to shard the table, basically. So actually, we did some experiment. So as long as the table size is not that large, actually the dense gradient communication gives rise a very good performance comparing with the sparse gradient communication. So the next one is the storage, the I/O system, where to store this data set. So we have multiple choices of I/O system for the data set. So the most intuitive one is we can download the dataset to a local SSD disk, which is available in the P4D instance on AWS. But this definitely has a size limitation, and also it is not easy to support multiple nodes because you need to do some shoveling of the data after each epochs. Another solution is S3 streaming. However, this has some performance throughput limitations. So finally, we seek for the solution which is called FX for Lustre as a dataset cache. So it is a global file system. So it definitely could support distributed training and shoveling as long as this instance is mounted into different nodes of your training system. Also, it has no storage scalability as long as you can apply for the unlimited space from the AWS. Another thing is the higher I/O throughput. So according to our statistics, our profilings, basically for each P4 node, like A100 GPU, we need around 2 to 5 gigabytes per second to saturate this edge GPU. This is really a challenge for a lot of file system. So due to the high cost of the FSX file system, so we actually use a feature from AWS, which is we can store the dataset in S3 and then use this as more like a cache. We can automatically sync the data when the training is started. When the training is finished, we release the data space, the storage space for other training jobs. Yeah, and then we have the data in the disk. So how do you move the data from the disk to GPU memory? This can be another challenge. So, so normally, like if you see like a lot of talking about like data pipeline, so we have batching, we have like shoveling, we have some pre-processing logics from the data set from the disk to the GPU memory. It's more like a last stage of the whole training system. So according to our some workload, 30% to 40% of the CPU are needed for data loading pre-processing to saturate a single GPU. But as you know, like we have 8 GPU in one box, but only have 96 CPUs. So basically, we only can saturate about like half of the GPUs in the P4 box. So I think the solution is like we try to offload the data loader to remote CPU. Basically, it's out of a box. So this kind of is more like a horizontal scaling of the input pipeline to resolve the I/O bottleneck. And also this decouples the data loading from the GPU training box. And also in some self-coordination and dynamic balancing for multiple GPUs. This is really a great fit of the array can help us. I think Pablo will give more details how this is implemented. So I think as a rule of thumb, we really need more CPUs to prepare the data for GPU, to move the data in the GPU memory. So the last one is one interesting problems we encounter in our productions. Basically, if we use some TensorFlow native like auto-tuning support, so of the data pipelines, so we frequently encounter a lot of crashes and even out of memory. So we have a study intern Kabir actually did some research in this area. So basically, we use the reinforcement learning to distribute the CPU resource in the training pipeline. Basically, it's more like we employ an agent, try to adjust basically the CPU resources in the training pipeline, and then we can get some feedback from the like the performance bottlenecks, feedback from the training system, and then try to tune this kind of pipeline to get the highest throughput. So if you want to know more detail, you can check this paper we published in Rexis this year. Yeah, I think the next part I will hand it over to my colleague Pablo. So he will talk about more like detailed implementation. Thanks.
Yeah, so the paper before is actually being presented right now in Singapore, in Rexis, at the same time, so coincidence. We do the ingestion of data from the file system. We need a lot of workers in CPU in order to get more threads to consume faster from the network. And we use this TF data experimental service provided by TensorFlow 2.9 and onwards that has a dispatcher and worker servers. The dispatcher is the one that coordinates between the workers, and the workers are the ones that actually execute the TF data pipeline in every processor. This has some advantages in making you go scale horizontal by just adding more workers and have the dispatch server coordinate between the different batches that comes from the workers to have with only one semantics, for example. What we have done is we wrap the whole idea of launching a dispatcher and worker as something called the data service. So when we instantiate the data service, we let Ray deploy the workers and the dispatcher in different nodes so we can capture more threads to read the data from. There are various ways we can use this. The first one is just create local workers. That means the dispatcher is deployed in the same node where the TensorFlow worker is deployed, and the data workers as well. So if you have remaining CPUs idle in the same box where you have the GPUs, you can deploy them there. There is an option to do this remotely. Just have the dispatcher in the same machine where the GPUs are, but the data workers live in an extra CPU box where you can use more threads. And there is the combination of both, like having local workers and remote workers all coordinated with the dispatcher. We're going to describe a little bit about the cluster infrastructure and how we deploy these clusters in the company. As follows, we will describe the cluster management, how we manage the resources, and how we integrate all of this with Ray. And in the end, how we practically use the training data storage and management. We call them the Manta Ray cluster. Quoting in Josh Wills, I'm very bad at naming, but I compensate that very good at caching validations. We have a managed infrastructure, correct? So we have a centralized place where we deploy the clusters, and we use an application called Spinnaker, which is open source. And this is the central point where we deploy all applications at Netflix. We use an immutable infrastructure. That means we bake AMIs, and we deploy complete machines already immutable. We use virtual machine isolation instead of Docker or container isolation. Our cluster deployments have a recipe to put all the software, base software in the machine already, such as the CUDA, cuDNN, Nickel libraries, the Python version and the Ray version that we use, and all the file system drivers to connect to external providers. We also have a notion of multi-tenant, and multi-tenant in the sense that we have a single cluster that runs all the jobs at the same time. So we have all our jobs lives in a monorepo that has the great feature that we can fix the version of Python, the version of Ray, and also the version of the entire set of dependencies. So they are immutable for as long as we have deployed all the workflows. And we run hundreds of jobs per day, which have a duration between 1 and 10 hours. These clusters are also heterogeneous, meaning that we have a head node, and then we have resource pools. And a resource pool is a group of machines that can auto-scale automatically. So we have CPU instances that can be used for consuming these workers that read from the file system. We have NVIDIA 800 GPUs that are meant to be used in a single GPU case. NVIDIA's 800 that are meant to be used in a multi-node or multi-GPU setting. And all of the clusters have EFS, which is an elastic NFS file system to store metadata, checkpoints, log, and output of the trainings. And we have this FSX for Lustre, which my colleague described as a high throughput file system for reading data. In a picture, it looks like this. We have Spinnaker lets you organize in auto-scaling groups because we deploy everything here in AWS. So the worker pools are uniform on the machine type. So we have a worker pool for 800s. You see the dots represent that they are auto-scalable. We don't auto-scale because we have a fixed number of machines, but they have the capability of auto-scaling if we wish so. We can auto-scale also the 800, 810, and the CPU-only workers. All of the clusters, all of the nodes in the cluster share this EFS file system for writing data and the FSX file system for reading the data at speed. On the lifetime of resources, we decided on a strategy of deploying durable clusters instead of ephemeral clusters. Durable clusters mean that we set up a cluster for at the beginning of the trainings, and when the cluster remain up and ready to receive all jobs. And then all the daily jobs that come to the cluster execute one after the other until the 24-hour cycle finishes. In order to have the training job fresh, we need to retrain them over and over at a 24-hour cycle. These clusters are maintained independently, and they are stable, and we reconfigure and upgrade them only at a different cadence, slower than we configure the jobs. So this is typically weekly or even monthly at some point. This approach has the advantage that all the training jobs come to the platform and train and live, and you don't have to wait for the upfront time to launch the cluster and be sure that it's ready for you to deploy your jobs. Also, it's quicker for deployment, and it has a simpler version matrix because we support only one version of Python, only one version of Ray, and only one version of the set of dependencies. And it has reduced maintenance for the team. On the resource sharing, there are several models that people apply on clusters. There are clusters that share nothing. That means you have a launch script that deploys the cluster, and then one cluster, one job. So one job needs a cluster. And then there's also the model for sharing all. So you have a unified big cluster, and all the jobs share it. We opted for the middle ground, which is shared by team. We have different teams get the use of different clusters that we deploy for them. And every team uses that cluster for a longer period of time. We use Spinnaker, that we said, in order to deploy these clusters. And having the share by team has some advantages, like we say, all the members of that team, all the workflows that run from the same team usually have the same dependencies, so running one after the other, it's not a problem. But it has the drawback that if you have two disjoint teams, if one team has resources available, the other team cannot use those resources. And we're working on a central scheduler and a queue. My colleague Kedar, he's in the audience. And we expect to have this central scheduler to be a router which will move the jobs to different clusters when the resources are available. Another thing that we do is we try to reduce the problem of specifying resources to run our jobs. Instead of combining all the dimensions, so my job needs this much RAM, this many CPUs, this many GPUs, we only specify GPUs. And we say we have a pool of single GPU usage and another pool for a GPU usage. And you have the constraint that when you launch a job, you can only specify how many GPUs you need. Everything else is determined by a predefined by the cluster management people. So the jobs that can run in this cluster can be either one GPU, 8 GPUs, or multiples of 8, 16, 24, etc. This turns an n-dimensional problem into a one-dimensional problem, so it's tractable for us to do the scheduling. This simplified resource scheduling is also reduce the toll cognitive toll on the researchers who need to launch jobs. Because instead of remembering how much RAM do I need to allocate or how many CPUs do I need for this particular job, they only allocate by how many GPUs of a certain type I need, and everything else is given by default. Remember that every instance in AWS has different CPU to memory ratio. Another example is that in the case of A100, the P4 instances have only 8 GPUs. And they are meant to be used at once, the 8 GPUs at once, because they are linked with the NVLink, which is a high bandwidth communication between GPUs. So we meant to be used these machines by 8 GPUs at a time. In the case of the CPU only, we also use one dimension, which is the number of CPUs that you need, instead of also specifying the RAM or the network. Here we describe a little bit in words, but I will switch to a picture. As my colleague described, we use FSX, the file system, with a backup on S3. That means we have all the pipelines that produce data in the company that are in different clusters in a different environment with a different scheduler, produce and materialize the data that lives in S3. And we ask them to toss the data into a certain bucket, and this bucket is synchronized with FSX. So for the training cluster view, when you deploy a job, you have the data immediately available in a POSIX location in a file system, /FSX/something. So we decouple the data producing cluster, or the data producing jobs, with the training jobs by having this instant synchronization between FSX and SA. Future work, as I said, we have a mixture of client mode to access the cluster for interactive jobs and submission jobs. We will try to go on job submission only. We are deploying currently a job scheduler that will act as a central entry point for all the clusters. It will also act as a router or as a queue. With pluggable policies, so we can then figure out how to maximize the use of the machines. And we are also exploring batch inference. using the actor pool in the array dataset pattern to do for the use case of evaluation or evaluation metrics. And I think that's all. We want to give special thanks to Si Shang and Matthew Deng, Richard Liu, which very kindly help us on the hi if you're watching us on all the channels and support. Thank you, and also for the people who are in the training platform here as well from Netflix. We are sitting in the audience. We have 4 minutes.
Yeah, 4 or 5 minutes for question.
Hi, great talk. So I have a couple questions about the frameworks. So first of all, for the TF data service, so that's something I want to like compare with the array data set, right? Why do you pick like the TF data service? What's the advantage it over the array data set? Because in my opinion, if you just want to orchestrate the remote worker, right, local worker, remote worker, the array data set can also do the similar thing. That's the first question. The second question, I'm also wondering, like in the beginning you mentioned about S3 streaming has a performance issue. Do you have any number? Like how, can you give us a little bit more like context about that? Like what's the performance issue you observe? And which drives you to use some kind of like cache using like file system?
It's a very long question. The first one is about why we prefer this versus, we don't have a preference. We just use this because we haven't explored rate dataset fully. And this we choose because it's TensorFlow specific and all the training jobs that needed are TensorFlow specific. But coming to your question, rate dataset is a very good option as well. You can use rate dataset to fetch the data and share the blocks in a no copy fashion with the arrow in flight. Using memory, so it's a very, very good option. Interestingly, we can probably use array datasets together with FSX or totally prescient of FSX and use array datasets only. But it's something that can be used, but we are not currently using. We are not using array dataset in that fashion. And you ask one more at the end, but
S3. So I can answer it. Yeah. I think like initially like I think S3 is good enough for T4 is low-end GPUs. For this high-end GPU, like we really need a lot of like CPUs. Maybe even it's more like a trade-off of the CPU resource basically. So let's say the FSX, because the I/O throughput is high, we may not need too many CPU to load the data. But if you plug in S3, then you in order to get like I just mentioned, like 2 to 5 gigabytes per second, is really a big challenge for S3 file system. Maybe you need like 100 CPU to load the data to get this high throughput. Yeah, I think for the first question is more like one thing to add is like I think when we started this project, the rate dataset is still not developed. Yeah, I think we can definitely impress that to see which one is more suitable, basically.
Yeah, also the TF dataset might work for all the frameworks, like PyTorch, for example. This one is only TensorFlow specific.
Hi, thank you for the great talk. I have a question on resource management. So you mentioned you allow teams to specify resources on the GPU dimension. So what would be your strategy when a user wants to use MIG-enabled instances or GPU sharing strategies?
Yeah, understand.
It's about the GPU sharing, basically. Yeah.
So there's a feature in NVIDIA GPUs called MIG, multi-instance GPU,
MIG?
or GPU sharing. If user wants to consume that, then what would be your strategy?
Yeah.
So we currently don't share GPUs, right? So we don't let users specify half of a GPU, correct? But if you want to use the utility that NVIDIA provides, which is MIG, you can partition a machine in physical or virtual GPUs. But for array, you can read them as physical. So let's say you partition all the GPUs by half, so you have double the number of GPUs. This strategy will work the same. You can deploy a pool of machines that are partitioned already beforehand, and then you can schedule jobs on them.
Yeah, I think like Washington, actually in the GPU-based training, I didn't see like people are trying to use the virtualizations. Basically because we have many strategies to get the GPU well utilized. For example, we can increase the batch size, right? We can also like use like the model paradigm. That's because the model is too large. So basically we have different ways to saturate the GPU during the training. So I didn't see a lot of example about like try to. I think in inference side.
And inference.
Yeah, there's still a lot of like this kind of improved utilizations by like doing the virtualization to split the GPU for multiple like usage.
Thank you.
That's sorry all the time we had for today, folks. Thank you all, and thank you again to the Netflix team.